Hello everyone, welcome to the presentation of the low-cost, high-precision sensor project team. Our team members are Zhaoqi, Xiaolei, Zhang, Zixuan, and Siru, Chen. Our client and sponsor is Dr. Zhenyu Zhang, and our technical advisor is Steven Natson. The aim of our project is to design and build a high-precision PM sensor out of cheap sensors, and the design can be further optimized for mass production. The successful development of this project will contribute to the widespread of home-use PM sensors and be helpful for researchers who wish to build a sensor network. Our expectation is to make a sensor that has a comparable performance with other sensors that cost multiple times ours, using filtering algorithms, offset algorithms, and machine learning. Furthermore, we wish to build an Android application that will be used to connect with the sensor for reading and tuning purposes. The app and the sensor should connect via Bluetooth for real-time reading, and an SD card should be used for transferring of historical data stored in the sensor. By the end of our project, we had successfully built the sensor, and it does output values close to another costlier PM sensors that we use for calibration. An aesthetically pleasing Android application had been developed, and it properly connects and reads from our sensor as expected. Now we will begin our demo.
Hello everyone again, I am Zhaoqi and I will be introducing about our final design. So this is our final design, this is our final sensing unit. Here, this device is our Sharp GP2Y 1026 digital sensor. Here is our Arduino unit used to receive and process the data. It is a Arduino MKR Wi-Fi 1010. This is our SD card reader loaded with a 2 GB SD card, and this, it may be a bit hard to see, but this over here is our Adafruit DHT11 temperature and humidity sensor. This over here is our reference PM sensor bought from a commercial site, and everything over here over this sensing unit is calibrated from with this as our reference. So now I'll begin demonstrating our sensed values. Our Arduino unit is now connected to my computer using serial port. The reason why I use serial port is because it is easier to print out multiple data, and I want to print out the sensed value before machine learning, after machine learning, and after the final calibration to make a comparison. Yeah, so as you can see here, my unit is already loaded with the program. Now, as you can see, our uncalibrated value, so the PM value before ML, ML stands for machine learning over here. So the value before ML is it's not as close as our value after machine learning as compared with the reference unit. Okay, so now I'll be showing how the sensor varies at a different environment. Again, I will be using the serial port. So this is a burning scene, something like a candle, but not exactly a candle, that is used to drive mosquitoes away in China. And it does diffuse some extent of PM 2.5 and PM 10. So now I'm holding the sensor close to it. It is not showing high values because the vapor or the fog does not flow through the air hole, and the sensor must have the air to flow through it to detect the PM value. So now I am holding it closer to it, and as you can see, it rises rapidly with the vapor going through the air hole of the sensor.
Hello everyone, I'm Zixuan. I will be showing the software application demo part of our project. The software application consists of 7 different components over here, and I divided them into 3 parts. Let's just go to part 1 first. Part 1 is basically the basic user authentication system of the application. Consists of login, sign up system, and we have a profile page, and also supplies offline mode, so the user do not have to sign in and rely on internet to log into our app. Okay, and then for the part 2 will be the real-time BLE data transfer page. I will introduce you guys about the main page functionality and the cloud database architecture. So the main page looks like this, and in order to connect to the sensor, we just need to click on it and choose the PM sensor we want, and then connect. And we just need to wait a bit till the phone actually receives the real-time data. Now it is. And if we go back to the Firebase database right now, you can see that under the user UID on the dataset, under the current date, there will be a buffer dataset showing here. And in order, if we don't want to create a buffer dataset and assign a unique name to it, as I just click on here, I click the start button and inputted the unique name you want this start button, and over here you see this new dataset 1 with the name I just inputted will be shown, so that this new dataset will be also stored. And to disconnect it, just need to click on this button again, and it's going to be disconnected. Okay, part 3 will be the part to view the data and load CSV file. I will introduce you guys about the data page and the functionality to load CSV file. This is our data page. We just go from the main page to this data page, and it's going to show the collected data sets and sorted by dates. And let's click on the recent one we did, and this is the recent dataset one we just collected. If you click on that, it's automatically gonna generate a graph. And to generate a graph for all, we just click on that button, and you see the x-axis are the dates and the y-axis are the average PM value on that date. Okay, for the load CSV file, we just need to click on this button here, and click on this load CSV file again, and choose the correct CSV file we want to generate graph, and the graph just shows up. Okay, let's continue to explore what have worked in the software and what didn't work in the software. First of all, what have worked, as I showed previously, the entire authentication system, including the login, sign-on, and profile page have worked. For the real-time data, the real-time BLE data transfer also worked to receive the data, and the cloud uploading system, if there is internet, also worked. For viewing the data and generating the graph, view the stored data on the cloud system is worked. The generating graph for each dataset is also working. Loading CSV file to generate a graph also worked. For what didn't work, we have two problems. First, we are unable to adjust the frequency from the phone to the sensor. The default frequency is always set to be once per 3 seconds. We have finished the basic structure of the function, like how to send and how to do with the receive the data. However, the sensor cannot receive the frequency values sent from the phone if the phone is receiving the real-time dataset from the sensor at the same time. Problem 2 is about the offline mode. Currently, offline mode is only partially down. We support connection between sensor and phone as well as receiving the real-time data under the offline mode. However, we are just unable to store and show the received data and generate them to graphs.
As shown in the demo, most of our hardware requirements were met. The sensor unit can properly read, filter, calibrate, and offset environmental variations, and finally gave us a result close to the sensors that we used for calibration. The Bluetooth connection also functioned as expected. Bluetooth on the sensor system will automatically start when the sensor starts. Connection with the app can be made whenever the user wishes to. For a more reliable connection, we also offer serial output from the Arduino so that the user can get a wired reading using a computer. The SD card is also functioning normally. The user can simply pop out the SD card from the sensor and insert it into an SD card reader or the phone's integrated reader to plot historical data stored in the sensor. Our prototype is also very portable as shown in the demo. Since we used a dynamic reading frequency, meaning that the sensor is expected to read less frequently when disconnected from the app, we anticipate the sensor's battery life to last over a month. During the development process, several hardware issues were encountered and remained unresolved. The most important one is that we could only use one PM sensor instead of 3 to properly sense data. Our original intention was to use 3 PM sensors to reduce part-to-part variation and further enhance precision, but sadly this did not work. This is because the first PM sensors that we used, the Sharp GP2Y 1014 analog PM sensors, weren't working as expected. The output voltage is both very small and inaccurate. Furthermore, the ADC of our Arduino is referencing a 3.3 internal voltage, yet the output range of the analog sensors is 5 volt. This mismatch also contributed to the malfunctioning of the system. We tried several ways to solve the issue, including connecting the sensors to an external voltage regulator and using an external 5-volt reference for the Arduino ADC, but none worked. The second iteration of our design was based on three Samyang DSM-501A digital sensors. Pulse width modulation was used to determine the PM density. We read the amount of time that the output signal from a sensor was 0 and divided that time by the sampling time to determine the PM density. We did some calibration to the system and made it functional. Xiaolei will demonstrate this later. Nevertheless, these sensors were not very compatible with our Arduino, resulting in inaccurate readings if Bluetooth was activated. Furthermore, these sensors require 1 minute of heating to circulate air. Hence, our final design is based on another sensor, the Sharp GP2Y 1026 PM sensor, which has its own built-in ADC and outputs a digital signal to represent the sensed voltage through the UART protocol. Unfortunately, our Arduino unit only allows one UART connection other than the serial connection with a computer. Hence, we could not use multiple PM sensors.
This is our advanced sensor fusion design. We used 3 digital output sensors with multivariable linear regression TensorFlow model inside. As we can see, under the clean air environment, the performance is very poor. This is because the model is just a simple multivariable linear regression model. It cannot accurately predict the PM value under the clean air condition. Because of the limited hardware resource on Arduino, we cannot run complex TensorFlow model in this design. This is how our system behaves under heavy smoke. The performance is much better than under clean air condition. Comparing this fusion version with our final prototype showed before, our final prototype has better stability and better cost effectiveness.
Hi everyone, I'm Siru Chen. I'll be presenting our future work and the conclusion. Our future work can be divided into 2 sections. It's just current design to finalize some leftover issues and add potential extensions and enhancements to improve performance and user experience. As previously mentioned, there are 3 features that are left undone due to time limits. The Bluetooth low energy locking is mainly due to a lack of experience with Bluetooth design. Now as we gain more understanding with Bluetooth low energy as well as generic attribute profile, the first step of future work is to fix the current Bluetooth low energy design to be able to send frequency to the sensor end. The offline mode is partially done and only requires slightly more time to be fully developed. The hardware end would have a possible change as well. The current one sensor system provides a decent feedback. However, if 3 sensor fusion system is needed, then our future work will include a research to reselect and replace the current hardware design. Now, let's talk about possible extensions and enhancement. Our project is a product-oriented project that a final working product with reasonable price and user-friendly feature is our main goal. Currently, we are working with Android platform. In our future work, we will design equivalent application for Apple iOS system to broaden our potential user population. Additionally, a Wi-Fi interface will be implemented. The current design requires users to manually store CSV file into their smartphone device for the application to process data. With a Wi-Fi interface, user can transmit the files through the Wi-Fi connection. This new extension is more intuitive and easy to use, which would greatly improve user experience. The potential enhancement for our future include a filtering algorithm enhancement and a prototype enhancement. By consulting electrical engineer to improve our current filtering algorithm, we'll be able to obtain a more accurate PM reading, and by finalizing our product with a custom printed circuit board to connect the microcontroller units, Bluetooth modulate, and sensors, will result in a reduction in size, weight, and cost. In conclusion, by incorporating our knowledge with hardware and software, our team developed a functional, low-cost, high-precision particulate matter sensors based on the net scattering detection method. A prototype system costs less than 100 Canadian dollars was designed, built, and tested for reading, processing, and communicating data. Net scattering PM sensors with temperature and humidity sensors was deployed to enhance the precision and reduce part-to-part variation in the hardware level. A 2-stage filtering algorithm was used to remove short-term noise, and a simple machine learning algorithm was developed to calibrate the PM sensors. The system was successfully built and tested to be meeting our initial requirements. And this is the end of our presentation. Thank you for listening, and now we are open for questions.